In this tape, we're going to take a closer look at the subject of system stability, and then go on to examine the role which protection schemes play in this. But first, what exactly do we mean by a stable or unstable system? Well, in simple terms, we refer to the power system as being stable when A, the power demands and losses on the system are being adequately supplied by the power being generated. This may include some power being imported from a neighboring utility. B, the frequency is stable and close to its nominal value. This is because power supply and power consumption are equal. C, the voltage is close to its nominal value at all points in the system. D, all of the transmission lines, transformers, generators, and other equipment are working within their rated capacity. Unfortunately, this perfect, steady-state condition rarely lasts for more than a few seconds, because the customer load demand is always changing. But these changes in load are relatively small, and moreover, they are usually anticipated according to the time of day and weather conditions. As a result, there is normally sufficient generating capacity online, and with the help of automatic equipment such as turbine governors and voltage regulators, the power supply can be quickly adjusted to meet the load demand. Adjustment of the turbine governor's set point regulates the mechanical energy input to the generator and consequently determines the electrical output. This situation is the same whether the generator is driven by a steam turbine, gas turbine, or a water turbine. It may take several seconds for governor adjustment to achieve the required change in generation, but this is quite adequate for normal minute-to-minute variations in load demand on the system. Similarly, the voltage regulators are relatively slow to adjust the excitation of the generators and so meet the change in demand for reactive power. So even in this steady-state, stable condition, slight changes are always occurring to the flow of real and reactive power along the transmission lines. Consequently, the load angle or power angle is also changing continuously. Now, what is this power angle? Well, in order to transmit power across a transmission line, in this example from bus 1 to bus 2, there must be a phase angle difference between the voltages V1 and V2 at each end. This is due to the inductive reactance XL of the transmission line. The resistance of the conductors is relatively small and is usually neglected in these studies. Let's look at a simple example of a single generator feeding a load through a single transmission line. If we consider the load demand at bus 2 to be at unity power factor, then the current is in phase with V2 as shown here. As this current flows through the transmission line, the inductive reactance produces a voltage drop, IXL, which is 90 degrees out of phase. As a result, the V2 voltage will lag with respect to V1. If the load demand at bus 2 increases, there will be an increase in current flow, so the voltage drop, IXL, increases like this. Consequently, the receiving end voltage, V2, lags further behind V1. The power angle, phi, increases as load increases. The value of the voltage drop, IXL, is approximately equal to V1 sine phi. Dividing this by XL, we can find the current. I equals V1 sine phi divided by XL. As power received is proportional to V2I, the amount of active power transferred along the transmission line is proportional to V1 times V2 sine phi divided by XL. Now let's look at the situation from the point of view of the sending end, that is, this generator, or perhaps several generators feeding the same bus. Normally, the generator is feeding into a very large power system. In order to transfer active power along the line, the voltage at this sending end must be leading that at the receiving end. This is in accordance with our power angle equation. In order to transfer more load along the line, the power angle must be increased by advancing the sending end voltage. This is achieved by increasing the energy input to the rotor. Studying the power angle equation, we can draw several important conclusions. The amount of power that can be transferred along a line can be increased by increasing the voltage. Of course, increasing the voltage implies that the transmission line hardware, insulators, and so on must be upgraded. But it does show one of the reasons why high voltage and extra high voltage is favored for transmission. It also shows why it's important that voltage levels must not be allowed to fall during operation. Another clear factor is the line inductive reactance. By reducing XL, we can increase the power capability of the line. An obvious example of this is when two lines run in parallel between two buses, so reducing the total impedance by half. This allows us to double the capacity of the circuit. But let's look at this other factor again, the power angle phi. This curve shows the transfer capability of the transmission line with relation to the power angle between the voltages at each end. When there is no angular displacement across the line, there will be no power flow. As the power angle increases, so does the load transfer. For example, where the angular displacement between the voltages is 30 degrees, then the power transfer across the line is equal to the sine of 30 degrees, that is 0.5 or 50%. At 90 degrees, the sine of the angle is equal to 1, so the load transfer is now maximum. If the angle increases beyond 90 degrees, then the load transfer begins to fall again because the sine of the angle diminishes. So here is an important conclusion. In order to increase the transfer of power across a transmission line, the power angle must be increased up to a limit of 90 degrees. If the power angle exceeds 90 degrees, then the power transfer will be reduced, and the system will probably fall out of synchronism. For stable operation, the system operator loads the system in such a manner that the load angle across each transmission line is much lower than 90 degrees. Let's look at a simple example. Here, the line is operating at approximately 40% capacity. The load angle across the line is about 25 degrees. In order to increase the load transfer, the operator must first increase the steam input to the turbine by adjusting the governor set point. This causes the rotor to accelerate and so advance the angle of voltage, V1. This now increases the power angle across the line and so increases the load transfer. After a brief oscillation, the governor settles down to its new position with the power angle now at, say, 45 degrees. What would be the situation if we had two identical transmission lines connected between the same buses instead of one? Now, the reactance between each end of the line is divided by 2, and therefore the transfer capability has been doubled for each particular angle of displacement. A new power angle curve can be drawn to represent this condition. On the curve, we can see that for every power transfer angle, the transfer capability has been doubled. For any particular value of load transfer, the load angle required is much less. Also, for any change in load, the required change in power angle is also much smaller. This means that with two lines in service, the operating point is a long way from the 90-degree limit of stability. It is apparent that this connection is more able to withstand fluctuations and remain stable than the single line connection. And for this reason, care must be taken when removing a line from service.